Recording in progress.
Hi, Ishan. Ishan, do you hear me?
Yeah, hi JP. Am I audible?
Yes, you are audible. How are you?
I'm fine. Actually, I just caught the flu 10 days back.
Oh, okay.
Yeah, but it's a normal flu. It's like normal cough cold.
Oh, okay. Hope you get it better soon. Hey,
Yeah,
Tarun.
fine.
Hey JP, hey Ishan. Sorry I'm late.
Yeah, no worries. How are you, Tarun?
Good JP. How are you?
I am good as well. Thank you,
Yeah,
Tarun.
yeah. I was at a workshop last week, so I couldn't attend. But if there's anything you want from me,
So
just let
actually,
me know. Yeah.
Bobby and I spoke, and
Mhm.
so we were just trying to figure out the interest, actually, how to about the participants. And I think there is some interest from applied materials, right? In terms of funding and supporting this project.
Oh,
But
okay.
I think we haven't heard them back, but they're kind of considering it. So that's where we are. Yeah, I don't know if Bob is going. I think Bob is traveling this week. He said he won't be joining. So he's attending that supercompute summit in Denver.
Mhm.
So yeah, in terms of update, I don't have anything further. Right, I think the next step is to gather interest and then meet with the people we talked about last time. Right, Bobby was mentioning the few companies interested. We meet with them and evangelize this idea. I think that's the next step.
Sounds good. Okay.
Yeah, so let's wait to hear from Bobby next week.
Mhm.
And then we can take it further.
Oh, sounds good, JP. Yeah.
Okay, and Tarun, today's agenda, what we want to cover is actually Ishan has wrote a paper on that power integrity analysis with chiplets,
Mhm.
the interop package that we developed. And he got some feedback from the committee, and then he wanted to discuss that.
Oh, sure. Yeah, definitely.
Yeah.
Yeah. I mean, yeah. I'll just listen through and then if
Yeah,
yeah,
please
yeah,
feel
yeah.
free to stay and comment, critique, and all that. But just want to let you know what the agenda is for today.
That sounds good, JP. Yeah. Thanks.
Yeah. So, hi Ishan, it's all yours. So, yeah, please go ahead.
Yeah, hi JP. Yeah, so there were mainly three broad points that were discussed in the reviewers' comments. So the first one I'll bring up is
Sorry, Ishan, before we get started, but so can you actually give a background to Tarun, like what the paper that you wrote and where you're publishing it?
okay. So as JP mentioned, I wrote a paper like we had performed the power integrity analysis on the Bow 1.0 chiplet links, where we had dies designed by BCA and D-Matrix. So um, I wrote a paper on how we did the power integrity, what all challenges we faced, and what all factors are to be taken into account while doing the analysis. And it was pretty elaborative on this particular topic. And the conference I submitted it to was the VLSI Design Conference, which is held in India annually. So in India, it's the largest VLSI conference, and it's an IEEE conference. And the paper got accepted actually, and I got the result about a month back. And there were some comments from the reviewers which I wanted to discuss with JP once. Yeah, the conference will be held in January, the second week of January, 6th to 10th. So, and that's about the
Okay.
background of the paper.
Yeah, thank you, Shan. So do you have to submit a revised paper or the
Yeah. So the
you have to-
revised paper deadline is this coming Monday. So they sent a link and instructions
Oh,
just
okay.
yesterday or
For
day
submitting
before.
the paper. Uh-huh.
Yeah. So I just wanted to make some changes regarding like surrounding these 3 points that I wanted to discuss today. And
Sure.
I'll
Yeah.
make those changes and some. And also, if you remember, I was doing another paper on a tape out part, if you remember, which I submitted in the same conference. Even that got accepted.
Mm-hmm.
I mean, there was another paper it was on a PAM4 transmitter, like a pretty basic one, but it was mainly more of a pseudo quaternary random sequence generator. So that was my second paper, so even that has been accepted.
Okay. Okay. That's good. Congratulations on both the papers.
Yeah, thank you, Jake.
Yeah, congrats.
Okay, so I'll bring up those 3 points. I'll just share those points in the chat box so that it's easier for you to even refer to.
Okay.
Yeah, I sent it on the chat.
Yeah, I think you pasted in the text
Yeah,
chat,
yes.
right? These are questions you got, is it? Okay.
Yeah, I've actually just summarized them. Like some of the reviewers had the same points, so I just did not repeat them. So the overall summary was basically these 3 points. I'll start with the third one since that is, I think, more simple. It says that the authors should elaborate more on the other work being done in this area and how it's different from other state-of-the-art techniques. So this was actually something I was expecting since we aren't showing any novelty in the technique. So
Mm.
this was more of a paper that's describing a tutorial on how to do it for chiplet links. So should I like add some text that indicates that this is just a tutorial in case somebody is looking for novelty? Like nobody should look if they look at it from that perspective. This is definitely a question that will come up.
No, this is not a question of novelty and all that,
Yeah.
but what they're asking you is actually, is there any work done in this area prior, right? So as far as we know, there are some work is done on chip. A lot of work has been done on non-chiplet links, right? And and then there is work on actually on the chiplet also. That I sent you on a reference, like what
Hmm.
I think Georgia Tech published a paper on, right, but not
Yeah.
specifically on power integrity, in general on power delivery on the chiplets, right? And this is
Hmm.
one. This is a paper. I mean, you can say that we actually focus exclusively on BOW based chiplets,
Okay.
right? So we should focus on our chiplets, and this is something unique. I haven't seen any publications in that direction. You can actually go to Google Scholar and search for this, and I haven't hit any. Right? Most of them focuses on the non-chiplet applications. So the unique
Okay.
aspect is this is actually a chiplet with the BOW links, and we are analyzing power integrity on the BOW, and that is unique.
But is the method any different? Or
Method can be same, right?
similar?
Method,
Okay.
all power integrity method are pretty similar. Everything's
Mhm.
same. That's not where focus is. We are showcasing
Yeah.
BOW chiplet power integrity analysis. That should be our focus.
Okay.
This is to serve as a reference for anybody doing chiplet link like UCAE or BOW,
Mhm.
and this will serve as a reference. It's not like we want to be something unique, novel method we want to highlight, right? That's not the purpose. The novelty is really the BOW.
Yeah, got it. So,
Right. So
and
yeah, so the does that answer question number 3, Tarun,
yes,
Ishan?
yeah. So also this like state of the art technique. So do they have different state of the art techniques, or is it like the only state of the art technique you would say is using like advanced tools that would do the power integrity for you? I mean the analysis for you, like let's say Power SI, or I think there's one more tool I can't recall, but I think there's
Sorry, say it one
one
more time.
like the third point also asks like how does it compare to existing state of the art techniques? So does that like state of the art techniques basically means using advanced tools, or is there?
No. State of art techniques is like what are techniques you're using? There's something special. There isn't any. This is an engineering effort, right? It's not something
Mhm.
very special. I mean, you can touch upon this, but you don't have to really address that particular point.
Okay. Mm.
State of art techniques. It's actually you can say the state of art technique. It's right. Extraction methodology tools you use are all state of art, but it's
Mhm.
very hard to quantify like all this. Oh, this is much state of art than what you
Yeah,
use,
yeah.
right? So
Mm.
yeah, you can actually don't have to address this specifically that part in more detail, right? As
Yeah.
long as you
Okay.
show some references what others have done, and then say this is for this is exclusively for BOW interface. Nobody has published before in the BOW interface, so this is a good reference for others to follow.
Yeah. Oh, yeah, got it. Yeah, just a minute. I'm just noting some points down.
Yeah, go ahead. Yeah, hi Trent. Trent, how are you doing?
Hello, sorry, took me a second there to go off of mute. Hello, I'm doing well, thank you.
Yeah, so Trent, in today's agenda, we're just reviewing the paper that what Ishan has submitted for the VLSI conference in India. It got accepted, and he has some review feedback he got. We're just going over the feedback.
Oh, okay.
Yeah, that's what it's for. This is done for the interop package.
Mhm.
And so also, last week you sent a message regarding the schedule, right? So I touched base with Boppy. I think Boppy is traveling this week.
Okay.
So maybe when he back here next week, we
Hmm.
can actually schedule a time. I mean, the same time next week we can discuss the schedule part.
Okay, yeah, schedule, and then yeah, I wanted to also discuss what aspects of the system still need support or funding, so that I can see about how NXP can contribute also, but I'll need a timeline for when that spend would be.
No,
So
that'd be
okay.
great. Yeah, thank you, Trent. I think we need Boppy for that. And also, I think there was an interest from applied materials as well. So we need to actually sync up with Boppy on those two aspects. So let's have a separate discussion next week.
Okay.
Yeah, thank you, Trent.
Mhm.
Go ahead, Ishan.
Yeah. So I'll move to the first point. So the first point is basically saying that like how in our case we use specific value decaps like 4.7 micro, 1 micro,
Hmm.
and 0.1 micro. So it says that typically they're used in a combination of like nanofarad and microfarad in parallel, because that that flattens your curve, the impedance curve, and gives a broadband impedance. So they're bringing up that point and asking how we basically came up with these
Yeah.
specific values of decaps and the number of decaps. Like if we could provide some intuition to the readers on
Sure.
how we
Yeah. So in actually what he's saying is correct. We kind of use a combination of values to right, and that is mostly done in the PCB world. In PCB, that you use like let's say from 100 microfarads all the way to let's say 0.1 microfarads, different values of capacitance, so that the impedance is actually kind of flattened, right? Smoothly flattened. So you don't have any anti-resonance.
Yeah.
So that was done in the board level, but not in the package level. The package level, you want to have more higher capacitance. Another reason is we can actually have different values of capacitance, right? Like let's say different locations of capacitor. You can have different values of capacitor, but the problem is it's really a manufacturing nightmare, because you have to keep an inventory and where should we populate what, right? It's not like PCB. So it's package.
The package.
If you have multiple values of capacitor, it becomes inventory management. Simplest thing to do is actually have one value of capacitor and populate uniformly. And that is what is done in 99% of the packages.
So the main issue is that it's very small and it's hard to manage the decaps at different locations.
Yeah,
level.
mainly for manufacturing reasons and inventory reasons, right? So in practice, that single value of capacitance really work at the package level.
Okay.
So if you have you tried different values, 0.11 and 4.7, and you found out like 4.7 is more optimal, right? The single value. You could optimize for multiple values, but that is actually defeats the manufacturing, right? We have more trouble with the manufacturing maintaining their inventory.
By maintaining the inventory, I mean, shouldn't that issue occur for the PCB level as well?
No, it's not an issue with the PCB level. The PCB level, anyway, you have a lot of components, right? And then these components are bigger and easier to handle. In the package, you have first of all to start itself is small, and then and putting in a small space like this, putting different values of capacitor, it's hard. It's not really required. It can be done, but it does not give you any additional advantage, and it actually brings more headache, because you have to maintain that. You need to know where you're populating what and maintain that inventory. In package, I mean, PCB is a large space, right? Package is small space. PCB is a large space. And you have pick and place machines. All this can handle really well. And you can generally you can have more capacitor, I mean, more values, more than one component.
Yeah, I got it.
It's not so much of a technical reason. It's more of a logistical reason.
Yeah.
And it's really not required. Even if you optimize it, if it comes out maybe it comes a little bit ahead, it won't give you a much technical advantage.
Yeah. So the second point is that the placement of the core vias and optimal selection and placement of decaps, and I think he maybe wants me to comment a little on how are we, like, just to maybe give some idea on the careful placement of core vias and I think the optimal selection of decaps is again, I think, discussed already. I think the expected current profiles that we would have for a particular package, like how do we maybe model those current profiles?
How do you model the current profile?
As in, what do we keep in mind while we model it, or are they like random, pseudo-random current profiles? Like, I mean, what should we expect from the current profile, like when we're modeling one?
Okay, let's take that part. I'm still not clear what it is. Let's discuss this. The first part you're asking is the careful, how do we place the core vias and capacitors, correct? And what is the optimization criteria use? Yeah, that is mainly we want, see, we can mainly we want to optimize the inductance, the loop inductance. The loop inductance should be very minimal. Right? We want to minimize the loop inductance, and to minimize the loop inductance, we need to have the core vias. We need lots of core vias, and then also we need the power next to a ground. Right. So if you have adjacent power and ground core vias, then you have a lower loop inductance. Right. If you only have all power vias and no ground vias, then you have a very high loop inductance. Right. So depending on the IP, that how the that VDD bump escapes, right? The placement of bumps. So this is actually, you need to place this core via for the power and ground adjacent to each other, and add as much as possible. Right. If you add too much, what will happen is it will actually impact these there are multiple rails. It will impact the second one, right? Another rail.
Yeah.
And it'll also actually cut the planes. So it's a kind of optimization game, trial and error optimization. And the whole goal is to minimize the loop inductance. Again, the placement of capacitor itself, we don't have much freedom. Unlike the PCB, you cannot keep the capacitor wherever we like because there are placement constraints. Right. So we need to place in such a way it does not impact the way we are placing the capacitor is we have capacitors in the top side and we have capacitors in the bottom BGA side. The top side capacitor locations we can place right next to the die edges. Right. So that location is because of the placement constraints of the die. We can only place at the periphery of the die edge. Right. And the bottom side capacitor, we have to remove the balls. So we have to remove some of the BGA balls to place these capacitors. Right. So again, this is an optimization game that if you have a lot of, let's say you have a lot of VDD and ground, and you remove some of these balls, VDD and ground balls, and you can use the capacitors. But you cannot remove too much of them because then it affects your power delivery. Right. So it's again trial and error. You actually remove some of the balls, fill it with capacitor and see how it impacts. If not, then if it's sufficient, leave it at that. If not, you have to move the capacitor, remove balls somewhere else, or remove more balls. Right? So it's a kind of optimization done to minimize the loop inductance. I think you have a curve that shows the loop inductance, right?
Yeah.
You can point to that.
I actually discussed the top side versus bottom side decap in the paper with figures, and I think we had discussed that where I highlighted the position of the placement of the caps from the layout.
So sorry?
In the paper, I actually highlighted the top and bottom side decaps, like this in the layout screenshot.
Right. Yeah.
Yeah. So I think maybe I have already discussed that, but still I think maybe they wanted something extra in the reviewers, but it's fine.
Yeah, you can mention this. This placement is done to minimize the loop inductance. And also the power delivery, right? That which should not impact your IR drop. If you remove too many balls, you create an IR drop problem. Right. And so it's a combination of the two, and it's done through an iterative process.
So in the bottom side, we replace the BGA balls with a decap, is what you're saying.
Correct. Yeah. So if you fill all with the balls, you cannot have any space for the cap. So you will have to remove some of the balls, and instead you place the capacitor.
Okay. Then we'll discuss the last part, the current profile.
Yeah, expected. What is the return? Expected current profile within the circuit to help meet the PX.
Even this particular point I had copy pasted from the comments. Even I wasn't sure why.
Staggering. See, the staggering is if all of them block currents are actually consuming at the same time, right? Then the peak actually goes up. Right. So this is actually a circuit design technique that you skew between different blocks. different blocks so that all the current consumption is not at the same point. Let's say a time is equal to 1 nanosecond, all the blocks consumes current, right? From let's say a clock is switching, now all the blocks is consuming current at exactly the rising edge of the clock, right? Then you'll have worst power integrity. So what the common technique to do is you have to actually kind of skew different block currents, not exactly at the clock, around the clock, maybe 5 seconds first block, 5 picoseconds first block, 100 picoseconds next block, something like this. So, right, so kind of even a small shift is going to help. So you don't get a sharp peak, but it's kind of more a flat peak. So it's called current shaping, and the current is shaped. So the block, this is done by the block design, like analog block design.
Yeah.
Right. Within that, you say E5 or the D2D, I mean the BOW5. This is taken care. If you don't have enough decap, you will have to stagger the current by skewing the clock so that they don't, all the currents don't align at the same time.
But otherwise, other than this, like an expected current profile is normally a typical, let's say like a random sequence. We don't,
Yeah,
or
it's
it's like application
correct,
specific.
yeah, it's a pseudo random sequence, correct.
Okay. Okay, fine. I think that's all I wanted to discuss.
Okay, sounds good.
But apart from the paper, a generic doubt I had is, as a feed designer, like, or like, what does an engineer basically work on when he works as a feed design engineer or something? Like, is he handling the SerDes design as well, or just at the, let's say, the system level where he designs protocols or interfacing, or
Sorry,
let's say,
Sean, I couldn't hear you. Can you say that one more time?
I'm asking that as a feed designer,
Uh,
what does an engineer basically work on? Like, does he work at the circuit or transistor level SerDes designing, or at a system level, does he work at how the interfacing will take place, what protocols will be involved in the data transfer or data communication? Or does he even work at, let's say, the SI and PI level?
No, it's all of those, right? The
Okay.
consists of all of those. So once a spec, I mean, let's say a standard like BOW spec is defined, then you'll have to the analog designers actually work at the signaling level, right? Like the clock recovery and the sampling, conversion
Yeah,
of digital to serial to parallel,
Mhm.
correct? And then training, but training
Equalization.
equalization and training the link, and these are purely analog, right?
But does this come under fee, or is this
Sorry,
something? So does this come under the fee, like as in phi, or is this something different?
no, it's all a part of 5. Yeah, the 5 has got analog portion as well as digital portion. So so the digital portion is typically done with the Verilog, but that interfaces with the analog circuits for a calibration training. Right, the analog portion takes care of the data recovery. Right, you have a clock and you have to sample it, converting that into a few, let's say 16 bits to, let's say, the bigger.
Yeah, there's a CDR and then a deserialization. Yeah.
Correct, serialization, deserialization,
Yeah.
and those are really analog domain.
Mhm. Okay. So phi is basically the broad level definition of all these particular tasks.
Sorry.
So phi is basically at the broad level definition, or the, you can say, the
Yeah.
title of
So yeah,
doing all
correct.
these.
It's a broad level definition. You need a circuit design, SIPI, and digital RTL level designers. Yeah,
Yeah.
it's a
Okay.
combination of all.
Yeah.
Okay.
Okay.
Anything else, Ishan? So so you will be giving a presentation, right? The ODSA Friday meeting.
Yeah, that would be on 8th December.
8th December, is it? Okay.
Hmm.
Okay, so
Yeah.
you'll be covering some of what you're publishing, correct?
Yes. As of now, I have my campus placements going on, and I think by maybe 2nd December I should be done with that. And
I
after
see.
that, I'll have to sit and make the presentation and exactly plan what to present.
Okay, okay. Okay, sure. Best wishes for your campus placements.
Yeah, thanks. Yeah.
Anything else, Ishan?
No, that's all.
Okay, in that case, then yeah, Tarun, Trent, is there anything from your side before we close the call?
Nope, nothing from me, JP. Yeah, sorry, I've been just a fly on the wall, but yeah.
Yeah, no
Yeah.
problem. Thanks for joining.
Nothing from me either, JP.
Okay, thanks, Trent, for joining today. So let's catch up the next week with Bobby. Thank you. Best wishes, Ishan. Bye.
Yeah, thanks, JP. Yeah,
Thank you.
one question, is this the link for all our successive meetings
Correct,
if
correct.
I
From
ever
now
want to join?
onwards, using Zoom actually, not that old GoToMeeting.
Okay. Fine.
Yeah,
I'll
same
save the
link I
link.
sent you. Yeah, the link does not change. It does not change.
Okay.
Yeah, thanks. Yeah, bye.
Yeah, bye. Yeah, bye everyone.